There's something like 80 slides in it, and I really thank all of you to come here and maybe possibly see many of those. I wrote something here which is familiar to many of us. Only when I started teaching, I did understand and mastered, I think, not yet mastered, to teach, but I mastered the subject. You know, mastering teaching is kind of tough. It takes a lot of years, a lot of practice. Some people are born talented teachers, and then therefore that's an added advantage. But these are very important for us. So you're right here, somewhere here, you do something, but we also encourage that you discuss and be a teacher. And that's when actually you can learn a lot of stuff, okay? Now, so most of our teachers, you know, when we were students, we had the same issues, same problems like most of you have. So the way I learn is different than the way some of you learn. So I'm going to discuss some of those. And I think I need to run this slide. We got many people who are behind this. Kettle, the provost, we got some grants from NSF, small grants, and then Engage, mini grant. And most importantly, I value the companies who donated a lot of parts and their failure stories, not the successful stories. I think that's very important. Many companies are not really willing to tell us this one. And that's why I request, and most of them actually provide that. And I'm really glad for that. And that's because of the students, you guys, okay? So you got a lot of power in you in the classroom, collectively, compared to me. So you need to take advantage of that. You need to express that you got the knowledge, collective knowledge, by discussions inside the classroom. And that will keep it active learning. And most of you do, okay? Again, as I said, there are a lot of slides I'll quickly run through. Statics OLI. If you go on to Statics Made Easy, you'll get 100 sites that says statistics. It's very difficult for you to find statics. Either it goes statistics all the time. Statistics made simple. I can guarantee that 80% of the time you get statistics, and which is very important, by the way. But statics is the one that you're looking at. OLI stands for Open Learning Initiative. It's an NSF. Carnegie Mellon University with Paul Stife has steered this collaborative grant. There's 6 of us, and we are one of them to basically disseminate and make it available to all the students of different departments to use these modules. Okay, so I'm going to show quickly those. And then that's what we start with. And I learned by touch and feel. So that's why I brought some components today. And I think most of you also probably like that. And learning just in time. And we'll discuss maybe depending on the time. I'm planning to do a grant later. At the end of the day, if you do have a textbook, and if you use it, and sometimes if you bring it to the classroom, and if you keep all your things ready to do the classwork, if you follow the lectures and see us during or after the lectures, normally if you pay attention, observe real life applications around us. There are many, many actually that Catherine can provide that you can relate to the class material and then discuss those. Then you'll enjoy teaching and learning. You don't have to come here today to listen to me because you already know stuff. So what I'm presenting is some opportunities that exist on the internet that you can probably read. This is just one of them, okay? Now, the first goal of this project, NSF project, collaborative grant, was to expand. There's some online versions, courseware in statics, developed by the project leaders who are Carnegie Mellon University. I'm part of it. So we develop some modules, give it to them. They develop a lot of them, much compared to that. And then we want to leverage the existing efforts on OLI, again, open learning initiatives, including the dashboard, digital dashboard. And the third goal has to gain insight into how this plays a role in student learning. And that's been an ongoing process. What we accomplished collectively, we don't teach much friction statics because of the short term. We only got 10 and a half weeks. We don't get much time to learn friction, but other colleges, they do teach friction. We do teach frames and machines, There's some modules in it. And there's something like 57,000 people who used this open courseware. So I'm going to try to launch it so you can see it. And actually, you can also meet me later so I can show you this. There are many, many courses, not just statics, that you can perhaps take a look at it. So there are many 9,000 users, registered users, and there are about 53 different institutions. The learning dashboard is the accomplishment for the collaborative. I'm not part of it. It's the Carnegie Mellon University. I mean, we can read this stuff. They're going to probably post those. So basically, the instructor may be able to utilize the class time to address some of the difficulties that the students are facing. Okay. Now, these modules, none of the modules actually replace an instructor or a textbook. We still need a textbook. We probably need an instructor. Now, these are definitely helpful as I say, flipped classroom. All right. Let me see if I can. So here is open learning initial courses. You can't read them, but it starts with American English, anatomy, French, psychology, chemistry, biology, statics is somewhere here, and there's many classes here. So you can go to any class, any one of these courses, you click on it, and then it opens something like this. For instance, in biochemistry, it gives an overview, and then you can see the course details. If you want the dashboard, that means you use it for the classroom. The students will go and log into the website, anonymous, no names in it, but you should put the names if you want the credit. So I use for extra credit for my classes. Statics is very important for us in mechanical engineering. So we use it in statics, we use it in solid mechanics, machine design, finite element analysis, fluid mechanics, you just name it. So we use everywhere statics. Okay? Statics is just state of equilibrium, and it's also used in electrical circuits. You got the huge branches circuits, they're all in equilibrium. Chemical engineering, we got that. HVAC, air conditioning, it's also equilibrium, right? So there are many, many places in which you can use equilibrium concepts. So the more you are thorough, not just for structural, but all other areas, I'll definitely help you with other classes. So those are the ones that, again, I can show you. We start with many questions, Freebody diagrams. We give some choices and basically pick the choice that represents the question, what exactly the question is asking. Okay. Now, my goal actually was to not just click it. If you click it, you get a wrong answer. Okay. Then it goes back to, I think that's a passive learning. That means, okay, click this choice. It comes, no, it's wrong. You go and read your free bodies. I don't want that. I wanted to use more depth. If I click on it, it tells, okay, it's wrong, and here is why. So if I can start making it rotate, suppose it's not balanced in rotation and falling down. If I can show it graphically, I couldn't do it. I tried it. We tried something when we had a colleague here in computer science, but we are going to do it someday. So if you click any of these images, it should be able to, if it is not balanced, it should start moving up, sideways, or rotate. So if I can do it, I think then there's no hint in it. It's not balanced already. So then you need to go back and think, and then maybe pick a better choice. So you're picking choices which are active. They're teaching something, not just say false or true. That's what we wanted to do, some graphics. And this dashboard tells us how much each student took to attempt the question to finish the quiz. In this case, there are 27 questions. Since 2006 or 2007, I started using these modules. And so over the years, many years, and most of the time I just give not all the modules, some modules for extra credit. Okay? Well, I know some students are weak in something during that term, so I assign those quizzes to be done by the students. I haven't done this year yet. Basic concepts. Go back to the Freebody diagrams, Newton's third law, and then roller joints, pin joints, and then, of course, we don't address too much friction. Friction is very important for us to know in upper level classes. And then, of course, the other things. Okay? Now the frequency of total scores, number of students. So on 27 questions, there's so many students who got Kettering, by the way, the good news, Kettering, compared to the other schools in our observation, Kettering is above average, much above average in basic statics. So I was very worried, but every year, when we do the statistics, Kettering comes out pretty good. It's not too bad, but we could do much better than that, okay? So these are 27 questions, who got it right in a sample. It's not just 2, so there's some multiplication factor in it. The concepts, those concepts I showed you before, and 0 out of 3, 3 out of 3 are correct with this bar. So you can see it's not too good. It's not too good, but it's not too bad either. You can see 0 out of 3 is more, the blue line. So these ones are not good. This again only for a couple of years. Now this is overall across 4 or 5 years. If I average those, 4 to 5 years. Now, these are the different quizzes, starting from equilibrium, basic equilibrium. I push you, you push me, right? Basic stuff, all the way up to moment of inertias that we use in statics. Everything is structural mechanics. So there are 19 quizzes. It takes a long time to do those. So I'm not really assigning all the quizzes. Maybe I assign here. Every time it comes back, initially it's okay. It could be better. But the average is right here, which is students have problems with couples and statically equivalent systems. That's very, very challenging for us to bring it up. The question is, how do you make them understand just in time, not through equations, not through homework, but physically, is it possible to do that? So there's some videos on the course outline, the OLI, the videos, some real life videos, examples, that might enhance. So this came pretty recent, the videos, probably a year ago. So I'm going to try those to basically raise this up. The most challenging stuff, internal loads, and that's going to be a nightmare. So for many students, even in all upper level classes, including the graduate level classes, internal forces, internal loads is very tough to understand by the students. So Freebody diagrams. So it's basically either they forget the movements, the forces, or they say, well, there's no force here, so that's a free body. And that's not correct, right? So again, I'm addressing the students. We know it as faculty. So how do you inbuild this? How do you encourage? How do you make the students understand? Don't do mistakes. How do they feel it for it? So that's very important, right? So same thing with the torques. Same thing with the torques, internal torques. So the internal forces, somehow, if you guys can help as students, the way you understand better that if we teach this way, you need to tell us by discussion, hey, I understand this better, you probably do it this way, because we teach our way, okay? And we try different things, but you should also respond and tell us, maybe in a different way we can teach you, right? For example, you can take breadsticks, you can cut it, you can twist those, use those. I use this sometimes often. Breadsticks, very important for me. If I cut a breadstick, you can see the cross section, you see bubbles, right? You see the bubbles in a breadstick. But you started with a dough, which is continuous body, it's a medium, like a dough, and that's continuous, right? You just do it, and then you fry it or bake it, and then it becomes a breadstick. I forgot to bring it today. You cut it, then you see the blowholes in it. Why? Well, heat is trapped inside, you got some bubbles. It's supposed to fluff, right? It's supposed to fluff. It's supposed to. Now, look at the shaft here. Now, this one is a solid object. It goes through many heat treatment processes. You can't see it. It's not often, but there are blowholes inside this. You can't see it, right? And then when you do the heat treatment processes, heat and cool, it's going to develop those cracks inside, okay? So you can do it by cutting it, doing metallography tests, but that's not easy for all the shafts. So the way to understand microscopic failures for the fatigue crack starts like a breadstick. Air is trapped, something is trapped inside. So it's not uniform body inside. So those demonstrations will definitely help the students. Now the top one, it's a favorite, right? So you got a P and a P force. What's the total force in the body? Then we get answers like 0 or twice P or P, So one of them is probably correct, depending on the question. The body is definitely in equilibrium, but one is the force, applied force, one is the reaction force. So that's something you need to understand that. Oh, I meant to talk about this, but compressive forces are possible. But internal loads are also important in HVAC applications, as I said before, right? Normally I do the demo to people just pulling one person in each hand. Then I say, okay, do you feel pain in your shoulders? Yes. Why? Because that's internal. You're in equilibrium. You're not moving this, you're not moving this, but your shoulders are in pain. So they're internal forces actually. That's a good demo of it, right? You can do it in the classroom, and that will probably help. Just this morning, you're going to balance this truck. How much does it weigh? 5,000 pounds, right? 5,000 pounds. And then this you see the air line, the air tube, that's actually lifting the whole truck, at least on one side. That's 3,000 pounds, right? One side, weight distribution. Now, we need to design this pipe. There's the pressure inside, a lot of pressure inside. When once you put enough pressure, the truck is now suspended, and then now it's in equilibrium by the action of the loads, etc. So I think some demos like this in the classroom early on in statics class. I'm talking about not upper level classes. Early on, if we can demonstrate some of these things, that will help the students understand in statics, whether they're in EE or IME, things will probably be better. They're called everyday examples. And that's what I'm going to talk about. Engage is, some of you heard it. Kettering is not new for this. It's called E-Cube lessons plans. Again, there are tons of classes in it, courses in it. Very good one, right? So this time we got a small grant, and I'm developing with the class everyday examples. So that, look at the classes here. There's so many classes. You can't read it. Elasticity, plasticity, dynamics, control systems, fluids. I know there's physics right here, right? We got chemistry. So I click on those, it says everyday examples. We do use it as instructors, but we want you to develop. So I developed like bookshelves for the classroom that students use. So light poles, bolts, we do a lot of that stuff, okay, for the classrooms. So I like the classroom location also. If a classroom is like this, that you can't see anything outside, to me it's not very learning. I mean, I can put equations and all that, but there's only limited stuff I can show. But if I see through a window, I love the business classrooms when I taught statics mechanics, because I can see the trees. The trees are in equilibrium. You cut the branch, the steel won't fall, right? It's still in equilibrium. It's going to grow another branch to balance it. So by nature, it's going to equilibrium. You can see a lot of stuff. In winter, we can see the poles, light poles. They're actually probably bending about 6 inches, 6 to 8 inches. So now you can demonstrate stuff when you're teaching the classroom. So I like those rooms with windows for me personally, or some gadgets like this. I think eventually we had a plan in mechanical to have all these toys kept in one room, like mechanics room, maybe lab. We're going to do that eventually someday. One is computational, virtual, one is real. I'm a real guy, plus computation too. Now, as I said, the bike pump wall, when we design pressure vessels, it's all real. So in the classroom, I use all this stuff by the students. Students go and find it, they do exercise, and then they use equations. Now the measurements is a little bit tough. We can do it. We got experimental stress analysis lab. We can do it, but the whole class is going to be tough. You can put strain gauges, you can measure the strain, and then of course you can measure the loads. We can do all that stuff. And again, as I said, Mohr circles and sausages, they go pretty close together. So there are a lot of stuff that you can teach with the everyday examples, right? As I said, touch, feel, and learn. I call it TOEFL. It's not the English TOEFL. Now, this is virtual, but they're real cylinders from Worthington Steels. They make different cylinders. They got the excellent facility I've ever seen in my life. These cylinders, they test those in bulletproof chamber. They call it 30 miles per hour bulletproof chambers, okay? And then you can see them bulging when they test those. I mean, I haven't seen it before. I mean, you can visually see the bulging steel cylinders. And then they take the measurements. So they really almost all cylinders, they test those for bulge testing. I couldn't take videos because they wouldn't allow that. But they are one of the co-op companies for us, Worthington Steels in Ohio. And I know this because my daughter and another student, they worked there. And they didn't like it because for the second term, they got them parking lot design, and they hated it. So I said, parking lot design is not easy, by the way. You can't just draw lines and call these parking lots. So, but they got one term parking lot, and they got frustrated, so they moved out. But I'm sorry to mention that, but Worthington Cylinder is one of the best companies. Now, students actually use those to do projects. We got this in the textbook, but that's real. Now, my thing is not the internet. Have you seen it? Have you experienced it, right? That's what I ask in my classes. So, yes, I have seen it on the internet, YouTube, so that's fine, but have you seen it yourself? Did you feel it? So that's the answer I want. And immediately students actually brought this, this term, bike projects. We got something right, small crank. It's right here. Andre, you got that right? Is that Andres? You guys? Okay, so it's a small crank. So that one is good. And I mean, but the students realize it's not for us to show them. So I told them, you go and get it. Now that's, of course, that's virtual. It's not very, it's okay, but all right, now 3D equilibrium bodies, right? We made models in the classroom. The students actually made those, not this term. Sometime back when I taught statics. Now 3D equilibrium is very tough. That's a virtual arrow, but it's a real apparatus. We have it in the lab. Anybody can use it. You can hang weights. I can change the location of this, the coordinates of this point. I can change 3D points. So in one day, we solved like 30 different problems. Each student comes, they sets their own dimensions. We solved 30 different problems because we can measure it right away, right? So it's pretty easy, and we can do it. We can make it better, but you know the students are wonderful students. They can make it. We got a lot of talented students on campus. We still need some facilities and help from technicians, and we are trying to work on it. I got a lot of stuff in my office, so Craig gracefully okayed for me to move to a new office because my office got junk with all this stuff. I still have a lot of stuff. I mean, I keep all those things. I love it. And soon I got to get rid of those someday. I got pipes from General Motors because they're doing the tube forming. So they need to test the tubes, right, to failure. So all these are donated by students and companies with failure reports. Now, those are the also tube forming. They are the forming. We're a company in near Delhi, somewhere in Michigan only. So I got all these parts available for any of you to see those. Okay. We got this in the ESL lab for the hydraulic. Now, conclusions are actually discussed. I'm requesting all the instructors and also the students, you discuss real-life applications, not just only internet, okay? And then you bring the real-life examples that are significant digits. Sometimes you need significant digits. If you look at Coke can, pop cans, pop can thickness is very small. When I was at Michigan Tech, they came with a project, the Coca-Cola company. They said if you can save 0.301, okay, that's inches. If you can save that material, 0.0001, they can save $1 billion per year by doing something, by stretch forming, etc. So they are looking at us to do stretch forming at Michigan Tech. So now the decimals are very important for Coke can, pop can. You all agree on it, right? So we can discuss those, you know. So 2.02 is not the same as 2.025 all of a sudden, right? So you can't round off decimals. We can discuss those in the classroom, right? And problem-based learning, project-based learnings, etc. Now the uncertainties in the classroom, uncertainties in design is a very important thing. The huge machines, such a virtual machine, a lot of components in it, a lot of uncertainties. Now some students are actually, when you take notes, it's very difficult to listen to me, people like me, and also take the notes because I speak fast. So one of the things I tell them is just, you know, understand, just listen to me and then take a picture of the board. So let's do it. I learned this from students from Hong Kong when I was teaching in Germany. So they are just listening. They took a picture of the board, go back and use it. Because now it's my handwriting. I can't go back if I did a mistake, because now it's photographed, right? I love that. That's a good practice. I love it. So continue to do that. Weight of the members, self-weight of the members. Now this one says, how much was it? 900 newtons. Do you have a feel for it? Oh, maybe 90 newtons, 900 newtons. Do you have a feel for it? I don't think so. How many of you have feel for some weights? Of course, we have our own weight, but not many of us, right? The students particularly. Now, I'm going to pass this around. It's heavy. This one is going to sit on a shaft. You see how wide it is? When we discuss the distributed loads, we always put the pointed loads like this. The load is distributed, right? And here is why. This is one of the examples. I'm going to pass it around. It's pretty heavy. So if you don't want to dirty your hands, just slide it, because it has some oil. Those are heavy components. Now, this one is only, how much do you think? Maybe 10 pounds, 15 pounds, 900 newtons. Just to give an example, you divide that by 5, actually 4 point something, to get pounds. So they're heavy guys. And look at the dimensions, 380. The students started solving problems. I said, hey, tell me how big it is by showing like this. They said, oh, like this? I said, no. Look at the dimensions here. 380, 760 millimeters is close to a meter. That big. So if you get a shaft diameter, I think I'm wrong, I guess. I got a huge number. Of course, you'll get a huge number because the pulleys are big, right? So how much you got, like? We don't remember now. I think maybe 4 inches, 3 to 4 inches. They are huge. You get huge shaft. Now look at the shaft. That's the one which goes with it. Another heavy stuff. Holly, you can take it?
It's too heavy for me.
It's too heavy for you, so okay. Now, broken components is from Borg-Warner Company. They donated this with history of how it failed. Can you break it like this in twisting? How much torque do you need to break it? Stress concentrations. You can show all this stuff in real life. A shaft is not 2 lines that we draw on a board. A shaft has a lot of components on it, a lot of features on it. So I would like you to feel it, if you like.
Break it. Don't break it.
It won't break. You can't break it. Now, talking about torsion, right? We say, okay, twist it. We show pictures. Now, here is a twisted bar. You can see the lines. It's real. Twisted bars here. Again, students donate this. So now, you can make calculations, how much torque is required to twist it. But in any case, touch and feel is my way of learning. I think students like it. Relearning from case studies. Again, I got a lot of students donate these parts from different stages. How the heads break for screws. Again, with a history. The students give me a history of those. And then, of course, we can use some virtual tools like deform to understand how the flow structure is, the metallurgical flow structure, the grain structure. If it is discontinuous, it's going to break right here, obviously. Now look at the bolts failed in fatigue at one of the hydroelectric dams in Russia, Shushenskoye, 2009. 63 people died. So I do discuss the case studies in the class. I asked the students to bring 1 case study, 2 case studies to the class, where that component, like a shaft or a gear or pulley, is a major reason why that failure occurred. We got tons of case studies, right? I bring those into the classroom, as many as possible, and discuss it. It's a beautiful dam. Number 2 station, bolts, things got actually started shaking up. They're huge. They're huge. Some of us are fortunate to have seen a powerhouse. But the students, not all students are that lucky to see all the powerhouses, right? So we need to bring something like this. They can probably get some experience out of it. That's a huge one. It's about 3 stories in a time. Francis turbines. Now, what do you think they failed? Of course, board fatigue, but why, right? It's all shambles. The reason for that is the uncertainty, assumptions. What's the assumption here? Well, you got the upstream water in hydroelectric power stations, upstream and downstream, right? The water is stored here, and then it comes to the Francis turbines. There are 9 of them. This is number 2. Now, the assumption was water is okay, water is pure, without contaminants. So they do have filters. Now, they know it, the water quality, they know it. They put filters in it, right? Now, how big filters can you put? Would you put a fine filter? Then the water will never flow through it with enough pressure. Now, they're bigger, right? Now, sometimes you do get bones in it from animals, cadavers. You get branches from the trees into the upstream, pebbles. So they're all uncertainties, right? Now, they did robust design with uncertainties, but still things start shaking, right? So how much can you design all these things? You can't. You can't make it perfect. But understanding uncertainties, discussing those in the classroom is very important, uncertainties, right? With all this, some students always ask for a key. May I have a key? I didn't understand what the student was asking. A key? You can't have keys to all the offices. Which one do you want anyway? You know, well, okay, wait a minute. You want the keys? I can give you keys to a room that we recently opened. It contains a lot of books in it. And guess what? It has books and also solution manuals to the older edition of the books. I don't think it's wrong. It's not the current one, but you know, they're all unpacked. It's been almost like how many, 6 months, 8 months, 1 year, still not unpacked. So students don't use it. Okay, you can't peel the banana and put it to your mouth, right? So you can come and take it, you take a look at it. We got a nice library, main library. You can use this anytime, 24 hours. The key is with us. So you got all the keys here, right? You get better answers. The last part, quickly, I don't know. We don't have time, is to somehow tie this up. Because Mo Torfa is angry with me if I don't do it, right? We need to submit at least one proposal. I ate a lot of lunches, so I need to submit something. So, no free lunches. I attended many I&D workshops, many innovation workshops. I attended many. So I think it's time to, I think we understand what they want in the topical grants. So I'm going to try to write a proposal. Uncertainties is one thing. Failures. We got too many flipped classrooms now, I think. Everybody's after flipped classrooms, like NABC analysis. So I don't know. So we need to do something a little bit new here. I'll try it. And the uncertainty is very important. So I'm going to use that and some of the videos that we have in the OLI modules and use the statics embedded with all these examples as instructional, maybe a flipped classroom for students who might have difficulties or who wants to preview it when they're at work before they take statics class. So I'm going to do that because we need this class, statics, well understood, because we need it for physics, we need it for mechanics materials, we need it for machine design, we need it for everybody as an engineer, right? Statics is very important. So we're trying our level best to give it to you continuously. We don't expect you to remember all that stuff, but at least you should do refresh continuously, okay, when you're at work. So hopefully I'll bring some modules to give it out to you, not to replace the class, but just a refresher, right, modules. So I'm going to do that in the form of the topical grant, but even if I don't get the grant, Mo, I can promise that I will continue to work on it, okay? All right. Engineers must accommodate uncertainty. It's very important for us. All of you know that, right? Those are working. Uncertainty always accompanies change. Material properties, I told you the hamburger or the, or the bread piece, they're not going to be same, right? Properties. Because we do thaw them, different heat treatment processes. There will be internal changes. It's very important for us to know those. I think I already talked about soda can, where it fits. It fits in all different materials, right? Finance, problems, optimization. And because it has economics, environmental issues that Professor Terry, she discussed in her class, a lot of issues in it, recycling. So Coke can itself, we can learn a lot of stuff, right? I think I already told you at the end, if you got a book, You don't need to come here, right? So there are a lot of e-courses available, tons of those. So I don't have textbook, Dr. E. I said, don't worry about it. Do you have internet? Yes. Please go there, right? Then, of course, you got everything in your hands. You don't need a textbook. So they're all the same, absolutely no difference. Yes, I'm going to assign problems from this book. I have to do it because that's a prescribed textbook. But hey, if you got another textbook, I'll give you another problem. It doesn't matter. It doesn't matter for me. I don't care, right? But a lot of resources are available. Don't take shelter that, hey, I don't have a textbook. Can I submit next week? That's okay once, but not too many times. Case studies, I told you I discussed those. And we published many papers in this area. And I'll be more than glad to share those with you, okay? Now, if you want to see the, I'll quickly try to fire up and see if it opens. Engineering Statistics Open Learning, ola.cmu.edu. They are blended learning things, learn with OLI, open learning initiatives, get to know about it, enter the course, Engineering Statistics. It requires something without an account. Then it opens up. There's 6 modules. There's 6, you can't read this. Module 1, Module 2, Module 9 now, right? There are many modules. Each module has a quiz. So if you click on couples, many of them have the videos, the definition of the couples. There are some online tests for you to understand. There are no equations. There are no numbers here, just the concepts to see if you understand couples, okay? And they do have videos, believe me. It may not work here, but we do have videos on those. And see, it's funny, it's trying to load up. They do work. If you apply force, they turn, they have some animations in it. You can't replace this with a regular class. You can't do it. But at least you can show the students, and they can go and do a supplement, right? Or you can ask them to pick some quizzes. But the important thing is we can gauge in which topics students are weak. That's the important thing with this dashboard thing, right? For that given class, which changes. Overall, we find that the internal forces, internal loads is the tough one for students to understand. So do the best that we can as instructors, real life examples, ask them how they understand that. And then I think that's one which will be a big service for all of us, internal forces, okay? I'm going to stop here, and if you got any questions or anything, I'm more than glad to answer that.
I have a small gift on behalf of panel. Thank you very much.
Thanks so much.